Welcome to our podcast, Artificial Intelligence, Papers and Concepts. I am Jack Malik, your AI-generated host, and with me is my AI-generated co-host, Sophia Lane.
Today we are going to dive into common pitfalls in computer vision and AI and how to avoid them. This is a report by BigVision.ai, a premier computer vision and AI consulting firm. Okay, let's unpack this. The core finding of this comprehensive report is, well, it's pretty sobering. Over 85% of AI initiatives fail to deliver their intended business value.
85%? That's huge.
It really is staggering. It means, for every 10 teams starting out, maybe 8 or 9 just don't get there, don't get the value they expected. So we're diving into what feels like a really pragmatic playbook. It's derived from real-world successes and, maybe more importantly, costly failures. We need to understand why these projects derail so often.
Exactly. And think of this deep dive as giving you, the listener, that essential pre-flight checklist you need to navigate an AI project successfully. We're going to hit the common pitfalls that pop up across the whole life cycle, really, from that first whiteboard idea all the way through to, managing logs and drift in production.
So it covers the full journey.
It does. And if you can sidestep these classic traps, you seriously increase your chances of actually delivering value. Let's start right at probably the most common failure point. Just defining what success even looks like.
Yeah, that brings us straight to pitfall 1, fuzzy problem definition and success criteria. It almost sounds too simple, like management 101 stuff. But in AI, it seems teams get so excited about the technology.
Oh, absolutely.
They jump into building the model, downloading data, running training loops, but without a really crisp, testable statement of the problem. Like, what decision is this model actually supposed to help with?
Right. And the avoidance strategy here is just intellectual rigor. Yeah. Right at step 1, you absolutely have to write a 1-page product requirements document, a PRD, and it needs to be ruthlessly clear. Not just listing features, I guess. No, not at all. It has to detail exactly who the user is, what decision the model informs, and crucially, what are the real quantifiable consequences if it gets it wrong. You have to translate those fuzzy business goals like improve efficiency into something you can actually measure.
Okay, can you give us a concrete example? How does that translation work in practice?
Sure. So instead of a vague goal like make our manual review process faster, the PRD target has to be something specific, like we will cut manual review time by 40% and critically add a guardrail at less than a 1% false positive rate.
Okay. So a clear target and a clear constraint.
Precisely. That gives you something concrete to aim for and measure against.
Right.
And always pre-commit to a single primary optimization metric. And then add your key engineering guardrails, things like maximum latency, cost per query, safety parameters, whatever is relevant.
Okay, and connecting that early definition to the actual metrics. This is where it gets really interesting, I think. Which takes us to pitfall 6. Misaligned metrics and thresholds. It seems like teams often optimize for, well, maybe easy metrics, like general AP or just plain accuracy.
Yeah, the standard academic metrics, vanity metrics sometimes.
Yeah, but the business doesn't run on accuracy alone. It runs on, the cost of errors or how many items a human reviewer can actually get through.
That's the core disconnect. You could have, say, a model with 99% accuracy. Sounds great. But if that 1% error represents a catastrophic false negative, maybe missing a critical security threat,
then it's potentially wiped out any value.
Exactly. It could cost the company far more than the project's worth. The solution here, and this is fascinating, involves actually converting those real-world business costs, dollar cost of a false positive versus the dollar cost of a false negative, into what's called a utility curve.
Okay, a utility curve. Sounds a bit academic. How do we, practically use that? How do dollars and risk translate to model tuning?
Think of it this way. Let's say a false negative, missing a defect, maybe costs $10,000 in recalls. But a false positive flagging something that's okay just costs $100 in extra inspection time.
Okay, big difference.
Huge difference. So your optimal operating point, the threshold you choose for your model, will need to aggressively minimize those expensive false negatives, even if that means you have to accept slightly more false positives, and maybe your overall F1 score isn't the theoretical maximum.
So the best business outcome isn't always the best algorithmic score.
Precisely. The utility curve shows you the threshold that delivers the maximum financial value. And another key point.
Yeah.
You absolutely must report metrics per segment.
Per segment? What do you mean?
Like per device type, per factory site, or even per demographic subgroup like skin tone.
Right. To catch biases.
Exactly. And you also need to track calibration. Use metrics like ECE or Breyer score.
Why is calibration so important? People usually talk about precision and recall.
Well, calibration tells you if your model knows when it doesn't know. If a model says it's 95% sure about something, is it actually right 95% of the time? If it says 95%, but it's only right 60% of the time, that's poor calibration. And that lack of reliability is a huge risk for safety, for trust, for any downstream decision.
That makes a total sense. Okay, moving beyond the foundations, let's get into the data itself, the data danger zone. Pitfall 2 is the classic one, unrepresentative training data. Your training set looks perfect, curated, clean, but it just doesn't match the messy reality of production. You're missing edge cases, weird lighting, different sensors.
Yeah, this is distribution shift, and it kills projects all the time. We saw a massive real-world example in 2020, didn't we?
With face masks.
Exactly. Face recognition systems trained on pre-pandemic data suddenly saw accuracy plummet when masks became common. The production reality shifted dramatically.
So how do you avoid that? You can't predict everything.
You can't predict everything, no. But you need to actively inventory the real-world conditions you do expect. Turn those findings into actual data requirements. Collect data deliberately, using techniques like stratification to ensure coverage. And actively look for the hard examples, hard negative mining. Crucially, build and maintain and version a dedicated edge case suite.
Like a special test set.
Yes, a permanent test set of known tricky examples that any new model must pass before it even gets considered for deployment.
Okay, so we collect great representative data, but then we can mess it up during preparation, right? That takes us to pitfall 3, label quality, leakage, and splits. Leakage sounds particularly nasty. It makes your offline metrics look amazing.
It does, gives you this totally false sense of confidence. You feel great about your model.
Until it hits the real world.
And fails spectacularly. Leakage happens when information from your test set accidentally contaminates your training set. Often it's subtle, like maybe the same person or the same background scene appears in both your training and testing splits.
How would you even know that's happening?
Well, there's a quick test you can run. Try building a really simple non-AI model, like a basic random forest, and train it only on metadata, things like image timestamps, maybe camera IDs, file sizes.
Okay.
If that simple metadata model performs suspiciously well on your test set, you probably have leakage. The metadata itself is giving away the answer.
Wow, that's a clever check. So how do we prevent this nightmare?
It's really twofold. First, label quality. You need crystal clear annotation guidelines with examples. And you have to track inter-annotator agreement. Humans make mistakes, introduce noise, you need to quantify it.
Right.
Second, and this is the most critical thing for preventing leakage, how you split your data.
Not just random splits then.
Absolutely not random splits. You need to split based on identity. Split by user, by patient, by scene, by session, by manufacturing batch. Whatever grouping makes sense to ensure independence, this guarantees a truly leakage-proof evaluation where your test set is genuinely unseen information.
Okay, let's shift gears slightly. Let's talk about where teams spend their effort. Pitfall 4 seems huge. Focusing on a model-centric approach instead of a data-centric one, teams spend sprint after sprint tweaking architectures, trying the latest fancy model, fiddling with hyperparameters.
Chasing those tiny percentage point gains.
Yeah, often for minimal, maybe not even statistically significant improvements.
Right, and that's because the returns you get from just tweaking the model architecture, they often hit a plateau really quickly. What's so compelling here is the power of the data-centric approach, where you treat the data itself as the product. That's where the highest leverage is. Dr. Andrew Ng shared some really powerful results on this.
Oh, yeah.
For a steel defect detection task, the baseline model accuracy was 76.2%. The team spent a bunch of time on model-centric stuff tweaking the architecture. 0% improvement. None. Then they shifted focus entirely to the data, cleaning labels, fixing the classification taxonomy, things like that. The result, a 16.9% improvement in accuracy.
16.9%. Just from fixing the data. That's incredible.
It really underscores the point.
So what's the immediate takeaway for an engineer listening right now? What should they do differently tomorrow?
So what is to? Start with small, fast models. Simple baselines.
Why small and fast?
Because they train quickly. It lets you iterate on your data quality much faster. Clean the data, retrain, evaluate, repeat. Only when your data quality metrics have truly plateaued, then consider scaling up the model capacity. Maybe try that bigger foundation model.
So data quality drives the process, not the model architecture.
Exactly. Data quality dictates progress.
Okay. Assuming we have good data now, let's look at what the model actually learns or thinks it's learning. Pitfall 5. Shortcut learning and spurious correlations. This is where the model kind of cheats, right?
Yeah, it finds lazy shortcuts. It latches onto things that happen to correlate with the label in the training data, but aren't the real cause. Things like a specific logo always appearing on defective products, or maybe a certain background color, or even a timestamp.
Instead of learning the actual visual features of the defect itself.
Precisely. It's not learning the concept you wanted to learn.
How do you even detect that?
You need forensic tools. Think of them as causal probes.
Right.
Use techniques like occlusion tests, cover up parts of the image, and see how the prediction changes. Use visualization tools like GradCam-style saliency maps to see where in the image the model's looking.
So you can literally see if it's focusing on the logo instead of the crack.
Exactly. If your medical AI is basing its diagnosis on the hospital name printed in the corner, you have a massive problem. You also need to proactively curate counterexamples.
What are those?
Samples that have the same correct label but appear in very different contexts. This forces the model to learn the intrinsic features, not just the context.
Right. And even if the model is learning the right things, we hit deployment reality. Pitfall 9, ignoring deployment constraints. This is the classic, well, it works on my machine problem. Chuckle slightly. Yeah. We've all been there or heard it. Your amazing model runs great on a giant workstation GPU.
But it completely melts the edge device it's supposed to run on. Or swamps the server because it's too slow.
Why does that happen so often?
Because the performance requirements. The service level objectives, or SLOs, weren't defined clearly right at the start.
Back to that upfront rigor again.
Absolutely. You must define those SLOs before you write a line of model code. What's the required latency? Not just average, but P95, 95% of queries must be faster than X milliseconds. What's the memory budget? The power draw limit. The maximum compiled model size.
And that influences your choices from day one.
Completely. It dictates your architecture choices. It forces you to plan the optimization path. Are you going to need quantization, pruning, distillation, and critically, profile the model early and often on the actual target hardware. Don't wait until the end.
Speaking of constraints and not overdoing it, let's hit Pitfall 7. Underpowered baselines and over-engineering. Seems related. Everyone wants to use the latest, biggest, shiniest model from the newest research paper.
Yeah, the temptation is strong, but don't start with that giant foundation model right out of the gate, because that complexity comes with immediate costs. Maintenance burden, inference latency, operational expense. It's crucial to establish strong, simple baselines first, like maybe a small standard CNN, or even just a linear classifier on top of a pre-trained frozen encoder.
Keep it simple initially.
Yes. And only add complexity if it gives you measurable, significant wins. Not just on your main metric, but also on those crucial guardrail metrics and evaluate it on your truly held-out test set.
And if the simple model is actually good enough?
Ship it. If it meets your business goals and your ROI target, get it out there faster and start reaping the benefits. Don't over-engineer for the sake of it.
That faster shipment needs guardrails, though, which brings us to maybe the most critical checks. Integrity and impact. Pitfall 11. Fairness, safety, and societal impact. This feels incredibly important. Just having a working model isn't enough if it works unfairly or causes harm.
Right. This can't be an afterthought.
No.
It requires a defined process, not just, good intentions. We've seen serious real-world consequences, like those dermatology AI systems.
Trained mostly on light skin images.
Exactly. And as a result, they drastically underperformed when evaluating conditions on darker skin types. The training data simply wasn't representative.
So what's the process to avoid that?
You need to define fairness guardrails before you even start collecting data. What are the critical subpopulations? And then you have to ensure you are proactively measuring and reporting segmented metrics. Break down performance across all relevant groups, demographics, device types, environments, whatever matters.
Catch those gaps before you deploy.
Yes, before it can cause harm.
Okay, so we ship a fair, well-tested model. Is the work done then?
Not even close. That brings us to Pitfall 10. Monitoring, drift, and silent failures.
The model that worked great on day one, but then slowly, silently got worse.
Maybe the input data characteristics change, that's data drift. Or maybe the underlying concept change, like what constitutes spam evolves over time. That's concept drift.
How do you fight the inevitable decay?
Rigorous MLOps discipline. Treat your deployed model like living software that needs constant care. You must continuously log the inputs the model sees and the scores it outputs. Track distribution, shifts in the inputs. Track changes in the output patterns. And maintaining a human-in-the-loop review process is often critical.
To catch weird cases.
Exactly. Sample predictions, especially low-confidence ones or ones near the decision boundary, have humans review and relabel them. Feed that back into retraining. And a golden rule for deployment: never just flip the switch to 100% production instantly.
Use shadow or canary deployments.
Yes, roll out gradually, monitor closely, and have automated rollback triggers ready if performance metrics suddenly drop below your SLOs.
Okay, let's bring it full circle. We started with business value.
There.
Let's end there too. Pitfall 16, ROI illusions. This seems like maybe the ultimate pitfall. Confusing model accuracy, even great accuracy, with actual return on investment.
It's incredibly common. Teams get focused on the leaderboard score.
And they forget, or maybe underestimate, the true costs.
Exactly. The cost of the cloud infrastructure, the ongoing cost of labeling for retraining, the cost of that human review team, the engineering cost of maintenance.
It all adds up.
It really does. You absolutely need to build a robust unit economics model before you decide to ship. Calculate the cost per prediction, the cost per image processed. Factor in the expected cost of errors using that utility curve we talked about earlier.
So you know the net value.
Precisely. And funding, project continuation. It should be stage-gated, based on demonstrated business impact in a pilot or shadow test. Not just because the accuracy number went up a point.
If the total cost of ownership outweighs the actual business benefit,
then the project is a failure, no matter how technically clever the model is.
Wow, that's a really comprehensive roadmap. Feels like we've covered the whole life cycle of potential disasters.
Yeah, and if you try to connect it all, see the bigger picture, the whole playbook really boils down to a few key themes. It's about prioritizing rigor over just moving fast. It's about treating every single phase from that first problem definition all the way to production logging with real engineering discipline. So when you start your next AI project, maybe run through that pre-flight checklist in your head. Do we have that crisp one-page PRD? Is it linked to a real financial utility curve? Are our data splits really leakage-proof? Do we have a plan for monitoring drift? Do we have a realistic ROI model?
That checklist seems essential. So what does this all mean for you listening? We learned from the source material, this Big Vision report, that especially in high-risk situations, it's often better for a model to just abstain, to say, I don't know, rather than making a confident mistake. And that raises a really important question, I think. If you can't clearly articulate exactly how your model is going to measurably improve that specific business metric you define, and if you can't say precisely how you'll know the moment its performance starts to degrade in the real world, are you actually ready to ship it? Maybe something to mull over as you plan your next AI venture. Thank you for joining us today. If you need help building AI products, please visit us at BigVision.ai. We also publish state-of-the-art computer vision and AI courses at OpenCV University.